Hello and welcome back to PC Retro Programmer. In the past couple of videos in this series, we've been looking at all of the assembly language instructions of the 8086 and 8088 that work with all of the general purpose registers, and of course with memory locations as well. Now you remember that the general purpose registers are these 8 at the top here, and of course the first 4 are further subdivided down into 8-bit registers. You have AH and AL, BH and BL, and so on. There's a high and a low byte in each case. And taken together, the 16 and 8-bit registers here are referred to as the general purpose registers. Of course, there's some other registers as well. There are the segment registers, of which there are 4, the flag register, and also the instruction pointer, which we don't use directly in assembly language. So in this video, what I want to do is focus on the instructions that are much more specialized in their use of registers. They don't just work with any old general purpose register, but they'll only work with specific registers. Now, of course, it'd be a very long video if I went into every single instruction in great detail, so I'm not going to do that. What I want to do is just introduce them briefly for a first time, just so that they seem more familiar when we see them in working code examples in later videos. And the other reason that I want to discuss these particular instructions is to really focus down on their specialized use of registers so that we can build up a picture of the specialized capabilities of each of the registers. Now before we get into that, there are actually a couple of instructions that we overlooked in the previous video, and these two actually work with all the general purpose registers and memory locations. So I'm going to introduce those first before we get into the more specialized ones. The first of these instructions that I want to look at is the negate instruction, and what this does is it flips the sign of a value in a register or a memory location. So let's take an example of this. I'm going to negate the AX register. So it'll flip the sign of the value in AX. Now what this is really doing internally in the CPU is it's subtracting AX from 0. But of course if you did that using a subtract instruction, you'd need another register to put the 0 in, and then the result would end up in that other register. And none of that's particularly convenient if you just want to flip the sign of something. So this instruction actually saves you quite a bit of work. So let's take a look at how it operates. I'll first of all put a value in AX. Let's say I put the value 1 in. So first of all, we'll just check there's a 1 in there. I'm just using a debug command to put it in, of course. And I'm just going to unassemble the code, and you can see neg AX there. The machine code for that is F7D8. Now, when I run this, what is going to be the result? Basically, what is -1 in binary? Well, the way to think about this is -1 is the value such that when you add 1 to it, you get 0. So which binary value, when you add 1 to it, is going to give you 0? Well, we can find out just by running that instruction, and let's see what it is. And as you can see, the result is FFFF. So basically, if I added a 1 to that value, you can see that I'd get carries all the way along, and everything would just be 0 at the end. So this is really -1 in binary. There's no minus signs in binary arithmetic. We have to use this 2's complement representation, as it's called, to represent negative values. So basically, to tell whether a value is negative or not, you just look at the top bit. If that's set, it's a negative value. Otherwise, it's 0 or positive. Now, there's one thing you have to be a little bit careful of. So let's put a different value in AX. I'm going to put the value 8000 in. And now let's negate that. So I'll just run out negate instruction again at address 0. And as you can see, it didn't change the value. We put 8000 in, and after negation, it's still 8000. And that's because when I add 8000 to itself in binary, I get all zeros. So it's its own negative in this 2's complement representation. Not very convenient because that doesn't really agree with arithmetic, but this is a special case that we just have to deal with specially. So one way you can deal with this is to consider it to be some kind of overflow, and basically you're going to need to have a larger register, maybe 32 bits instead of 16. And I'll talk about how to sign extend a register from 16 bits to 32 a little bit later. But basically this is a special case that you just have to deal with. All of the other values have distinct positive and negative values. Except for 0, of course, which again is its own negative. So that's the other value. But this makes sense arithmetically. Minus 0 is 0. Alright, so the other instruction I want to look at is the not instruction. So again, let's just assemble that. I'll just not the AX register. Of course, this works with any general purpose register or a memory location. And what this does is it flips all the bits of a register. So actually, let's just do that with our 8000 value and see what happens. So the result is 7FFF. So you can see 0 in binary is 0000, and if I flipped all the bits, that'd become 1111, which is F in hexadecimal. So all the zeros are going to become Fs, and the 8 is 1000 in binary, and if I flip all the bits, it's 0111, which is 7 in hexadecimal. So I get 7FFF. So that's the negate and the not instruction. Now the not instruction doesn't touch any flags. The negate instruction just adjusts the flags as though it was subtracting the value from 0. So basically, if you did a subtraction of that value from 0 using a subtract instruction, the flags would be changed in exactly the same way. So that's the 2 instructions that I missed. So now it's time to start looking at some of the more specialized instructions. Well, I already alluded to the sign extend instructions, so let's deal with those first. These are Cbw and Cwd, and I guess these are meant to stand for change byte to word and change word to double word. And so basically these are for upgrading values either from 8 bits to 16 bits in the case of Cbw, or 16 bits to 32 bits in the case of Cwd, and they keep the sign the same. That's the important feature. So the way these work is that they just look at the top bit. So if you had a negative value in AL, the top bit of AL would be a 1. And in order to change that into a 16-bit value, all you have to do is set all of the bits in AH to a 1. And that would upgrade that value. And similarly, if there was a 0 or positive value in AL, then the top bit would be a 0. And so it would just put that 0 in all of the bits of AH. And the same thing for Cwd. Just looks at the top bit of AX and puts that bit in all of the bits of DX. And that's exactly what you have to do to upgrade a signed value in binary. So let's just take a quick look at an example of one of these. I'm just going to do the Cwd one. And let's put a value in AX. Why not 8000? And when we run this, it's going to upgrade that, and you can see that the top bit of AX was a 1, and so it's just put all 1s in the DX register. And now that combination DX-AX is the 32-bit value that is arithmetically the same number as the 16-bit value that was in AX. Now, the important thing to realize about this instruction is that it's kind of thinking of DX and AX together as some kind of 32-bit accumulator. Now, of course, it's only a 16-bit processor, so there's only a handful of instructions that really think of DX, AX as a 32-bit accumulator. There's multiplication and division, and there's sign extension off the top of my head. This is one of the specialized purposes of the DX-AX combination, to be basically a 32-bit accumulator. Now, there's a bunch of really bizarre instructions which I just want to get out of the way, but unfortunately they're so convoluted, they're hard to describe in a single sentence. So let me describe them. There's ASCII adjust addition and ASCII adjust subtraction. For some bizarre reason, these expect that you started off with two ASCII values, ASCII codes, representing decimal digits 0 through 9, and for some strange reason you decided to add or subtract these using just an ordinary add or subtract instruction. And for some bizarre reason, you want the mangled result to be converted into a binary coded decimal value. Yeah, I said it was weird, it's weird. So let's see what binary coded decimal is, because maybe this is an important concept. So there are two forms, there's packed and unpacked. So in packed binary coded decimal, the value 1234 would be written 1, 2, 3, 4, just as you would do in decimal. So you just ignore the digits A through F in hexadecimal, and you just use the digits 0 through 9, and think of the values as being decimal values. Really nice to work with, but obviously computationally expensive. There's also an unpacked version, and so, for example, the value 12 would be written 01, 02, so you just put zeros in between. Now, these two instructions, they take the results and they convert them into unpacked binary coded decimal, and they assume that you start in the AL register and you end in the AL register. Now, they even will do a carry or a borrow into the AH register if there was a decimal carry or borrow. So really bizarre, but they can be useful if you're working a lot with ASCII digits. Now, DAA and DAS are kind of similar in a way, but they assume that you added or subtracted two packed binary coded decimal numbers in AL. So the result, again, is going to be messed up because the machine can only do binary arithmetic, not decimal arithmetic. And so these will unmangle the results so that you end up with a valid packed binary coded decimal value in the AL register. And of course any carry or borrow will just end up in the carry flag. And the final two bizarre instructions are basically for converting to and from unpacked binary coded decimal. And these are actually useful instructions, but maybe not for the reasons that you're thinking. So let's just cover the standard use of these. So the Aad instruction takes an unpacked binary coded decimal value in AX and converts it down to an ordinary binary value in AL, without restriction really. And the AAM instruction basically just goes back the other way. Now, AAM has an obvious limitation. If the value that you're going to end up with is more than 99 in decimal, you're not going to be able to fit the result in the AX register. You can only get 2 digits in unpacked BCD. And so what it does in that case is it gets the bottom digit correct and then just uses hexadecimal for the top digit. But anyway, these instructions don't really give away much from their names. So AAD is basically envisaging that you want to do a division of binary coded decimal values. So in order to do that, you're first going to have to convert to binary, and so that's what the instruction is for. And the AAM instruction envisages that you're trying to multiply two binary coded decimal digits. And obviously if you just do that using the multiply instruction, you'll end up with just an ordinary binary value. So if you want to get the unpacked BCD result, you have to convert from binary back into unpacked BCD. And so that's what they're envisaging that you're going to use these for. But it turns out these instructions have some hidden undocumented power The second byte of machine code for each of these instructions is actually just the value 10. But you don't need to use the value 10. You can actually change that byte. And so basically what AAD does is that it multiplies the AH register by that byte of machine code and adds the AL register. And the AAM instruction divides the AL register by that byte of machine code and stores the quotient in AH and the remainder in AL. In other words, you can do a multiply and add instruction with AAD with a constant multiplier, and with AAM you can do a division with remainder by a constant. So these are actually very useful operations and probably really make the topic for an entire video of their own. The next block of instructions are pretty important. They're arithmetic instructions, and they're for multiplication and division. Now, there are actually two different versions of these. There's two instructions for unsigned operations and two for signed operations. And these are quite useful, but very, very slow. They can take 120 or even 150 or 160 cycles if you're dealing with memory. And so these are often not used where it's possible to use some shifts and adds instead. Basically, you want to try and avoid these if you possibly can. Now, a situation where you wouldn't want to avoid this is if you were multiplying or dividing by a variable value that could take any value. Normally, when you're multiplying or dividing by a constant, that's when you'll often find an alternative like shifts and adds and subtracts and so on. And the reason for all this is that mul and div are actually coded inside the CPU as little programs inside the microcode ROM of the CPU. And so it's actually just running a little program using more simple instructions, and it really can't do better than what you can do by hand if you're multiplying or dividing by a constant. So the way this works is that the mul instruction would start with an 8-bit value in the AL register, and it will allow you to multiply that by any other general purpose 8-bit register. And the result will end up in AX. So it's an 8 to 16-bit multiply. Similarly, you could start with a 16-bit value in the AX register and another 16-bit value in any other 16-bit general purpose register, and it'll multiply them together and put the result, which is 32 bits, into DX-AX. So this is really a very special instruction because it's really allowing you to do 16 to 32-bit multiplication, which is quite a surprise that this CPU supported this. So div basically works the other way around. So it would start with a 16-bit value in AX, and it'll allow you to divide by an 8-bit value in some other 8-bit general purpose register, and it'll put the result, the quotient, into the AL register. And as it happens, it also computes the remainder for you and puts it in the AH register. And similarly, if you start with a 32-bit value in DX-AX with the high 16 bits in DX, and then you divide by another 16-bit general purpose register, it will put the result, the quotient, into the AX register, and as it happens, it'll also compute the remainder, and it puts that in the DX register for you. So there are unsigned versions and there are signed versions of these. Basically, in both cases, you have to be careful with div. And let me explain why that is. Basically, if I start off with a 16-bit value that's very large and an 8-bit value which is very small, the quotient won't fit in AL. So when that's the case, it raises a divide by 0 interrupt. And so you'll often see a message on the screen that you divided by 0. It's actually not necessarily that you did divide by 0, but when it can't fit the result in the AL register, then it will raise this exception. And similarly, if I start with a very large 32-bit value and a very small 16-bit value, then it won't be able to fit the quotient in AX, and so again you get a divide by zero error. So that's something to watch out for with div and idiv. One way around this actually is just to shift the divisor to the left so it's larger, and then you can fit the result in AL or AX, depending what version you're using, and then you just shift that result once you're done. So that's the mul and div instructions. I'm just going to give one example of this just so you can see how it works. And I'll use the div instruction, and I'll use dx ax divided by some other register. So let's first of all put some values in dx and ax. So in dx I'm just going to put the value 1, and in ax I'll put the value, let's say FFFF. And then I'm going to put a value in bx, so this is going to be my divisor, and let's just put the value 0032, that should do the job. And now I'm going to assemble my instruction, which is just div bx. So I don't need to tell it where the dividend is, because this is fixed. It has to be in dx ax. I only need to tell it where the divisor is, that's in bx. And so there's only one operand to this instruction. So now let's run this. It's going to divide the 32-bit value 0001FFFF by the 16-bit value 0032. And let's see what it does. And the result apparently is OA3D, that's the quotient, and the remainder was 0015. You can see the remainder in the DX register there. So that's how div works.